Welcome in another video. Today we will discuss the difference between paramagnetism and diamagnetism. So let's get started. Paramagnetism or paramagnetic compounds are compounds that are attracted to the external magnetic field due to the existence of unpaired or single electrons in their orbitals. However, diamagnetic compounds, they repel. You can see the difference here. Paramagnetic compounds are attracted to the magnetic field, while the diamagnetic compounds are repelled by the magnetic field. You get me? Due to the existence of paired electrons. So all of the electrons in their orbitals are paired. You got me right? So let's take some examples. We start with scandium-21. If you to configure the electrons of scandium-21, we would see something like this. Argon 18, then 4s2, then 3d1. What you can see here, you can see all of the electrons starting from the 1s up to 4s2. You can see that they are paired electrons, right? While in the 3D sublevel, you can see only one electron. So you have only one unpaired electron. Let's draw it just like this. The 5 orbitals of the 3D of the scandium. So we have here 3D, and we have only one electron left in the sublevel 3D. So this should be paramagnetic or diamagnetic. Okay, this should be paramagnetic. Why? Because you only have one unpaired electron in the 3D sublevel. You got me? Okay, you have at least one unpaired electron. If you have like two unpaired electrons, three unpaired electrons, four unpaired electrons, five unpaired electrons, that's okay. But if you have no unpaired electrons at all, that means you have a diamagnetic compound. You got me right. So let's check the scandium 3 positive, but let's electron configure the scandium 3 positive from the beginning, okay? So we start with 1s2, 2s2, 2p6, 2p6, 3s2, 3p6. Okay, we have here 4 plus 6, 10. 10 plus 8, that means we have 18 electrons. So this is scandium 3 positive because you lose 3 electrons. You lose the electrons of the 4s2 and you lose the electrons of 3d1. In total, the 3 electrons are lost from the scandium. So you will get the electronic configuration of argon 18. So what you can see here, you can see that you don't have any unpaired electrons or single electrons, right? So this should be diamagnetic compound. Let's write it down. So this should be paramagnetic. This is paramagnetic, and this should be diamagnetic. Diamagnetic. Okay, so let's move on to chromium 3 positive. Okay, I will I will just electron configure the chromium metal first, then I will move to chromium 3 positive, okay? So if I were to electron configure chromium, chromium is 24. Let's start with argon 18, then 4s2, 3d 3D, sorry, 3D 4. But the electronic configuration here is not correct, right? It should be 4s1, 3d5. That makes the 3D sublevel more stable, right? So let's look here. We want to lose how many electrons? 3 electrons, right? We need to lose 3 electrons to get chromium 3 positive, right? So this should be removed, and 2 more electrons should be removed from the 3D sublevel. So you will end up with 3D3, right? 3D3. 3D3. Oh, what is the problem? Okay. 3d3. Okay, so you have 3d3, and let's draw the orbitals just like this. So you have three electrons left here. So what do you think? Paramagnetic or diamagnetic? Hmm, this should be, of course, paramagnetic, paramagnetic compound. Why? Because you have three unpaired electrons, right? If you don't have any unpaired electrons, you would end up with diamagnetic compound. So let's move into the electronic configuration of copper. Normally copper 29, let's electron configure copper 29 first, the metal itself, then we will check the copper 1 positive, right? So I will just electron configure the copper 29 first. So we have argon 18, then 4s2, then 3d9, but this is not stable electronic configuration. This is not the stable electronic configuration of copper metal, copper zero, right? So what happens here, one electron from the 4s travels to the 3d sublevel, and you end up with 4s1 3d 10 electronic configuration. So I want to have only copper 1 positive, right? So this will be cancelled out. So you will end up with argon 18 3d10. So let's draw the um, the orbitals of the 3d sublevel. It will be like this. So you have 10 electrons. You have to electron configure the single electrons first. You have to draw the single electrons first according to Hund's rule. Then you pair them, right? You do the pairing, right? So when you do the pairing, you end up with 10 electrons in the 3d sublevel. That means you have a diamagnetic compound. But the copper here, I mean, this is not a compound, this is iron. So the iron itself is diamagnetic, right? So, so what about nickel 2 positive? Hmm? Nickel, nickel 29, 28. When you electron configure nickel 28, you start with argon 18, then 4s2, 3d8. And this is correct electronic configuration, but you have to lose, but here we need to get rid of two electrons from the nickel, and when you get rid of two electrons, you lose the electrons from the 4s sublevel, not the 3d sublevel. So this will be canceled out, the 4s. Then you end up with 3d8, right? When you draw, let me draw the nickel here because we don't have more space. So sorry for that, but we don't have more space here. Let me draw it here. 1, 2, 3, 4, 5. You have 8 electrons. So 1, 2, 3, 4, 5, 6, 7, and 8. Okay. How many unpaired electrons left? You have 2 unpaired electrons left, right? So this should be directly paramagnetic, right? Paramagnetic. This is a paramagnetic uh, compound, right? Okay, so we move on to the magnetic moment. What is the magnetic moment? It's so so I need to pause it for a second. So the magnetic moment is a property by which we can determine the number of unpaired electrons or the single electrons in the iron or the metal. So we can get an overview of the electronic structure of this metal or the ion. So magnetic moment is equal to the square root of n times n plus 2. So n, where n is the number of unpaired electrons. Okay? Okay, so let's apply it here. Let's apply it. What is the magnetic moment of scandium? Scandium. Let's say scandium here. So mu is equal to the square root of n times n plus 2. Let's see here. How many single electrons here? We have only one. So 1 times 1 plus 2. That would be 1 times 3. So this is the square root of 3 Bohr's magneton. Uh, this is the unit of the magnetic moment. So let's check another example. We have chromium 3 positive. What is the mu here? So mu here is equal to the square root of n. How many n here? How many unpaired electrons here? We have 3. 3 times 3 plus 2, which is equal to the square root of 3. This is 5. 3 times 5, which is equal to the square root of 15 Bohr's magneton. And then here we have here the copper 1 positive. What is the magnetic moment here? What is the mu or the magnetic moment of copper 1 positive? Mu here is 0, is equal to 0. Why? Because we don't have any electrons, right? Any single electrons, right? We have only paired electrons. How about nickel 2 positive? How many single electrons here? Here we have one single electrons and another single electron. So if you to calculate the nickel 2 positive, I will write it down here. So mu for nickel 2 positive is equal to the square root of 2 times 2 plus 2, which is equal to how much? Let's see how many. So 2 plus 2, 4. 4 times 2, which is 8. So the square root of 8 Bohr's magneton. I hope you understand it. I hope you understood it correctly. And see you in the next video. Bye.